Sign language relies on a continuous flow of movement, space, and rhythm, rather than static hand shapes. To recognize it automatically, a system has to map the spatio-temporal motion of the signer in real time. In many parts of the Global South, inclusive healthcare clinics need this technology the most, but to guarantee patient privacy and function reliably without internet connectivity, the processing has to happen entirely offline, directly on the local hardware. The most accurate dynamic sign language recognition systems use massive 3D convolutional neural networks or transformer architectures. They require server-class GPUs and gigabytes of memory to process video sequences. This visualization compares the memory footprint of those server-class models to a standard edge device. A typical Cortex-M microcontroller operates under strict physical limits, less than 1 megabyte of flash storage for the software, and a few hundred kilobytes of SRAM for active memory. You cannot simply compress a cloud-based video model to fit that space. The raw memory required to analyze three-dimensional motion across dozens of frames exceeds the hardware's physical capacity long before the analysis even begins. Taking existing state-of-the-art models and shrinking them down structurally fails. Offline sign language recognition requires rewriting the mathematical approach entirely. Writing software for a microcontroller requires compiling the logic into a constrained inference stack, a highly optimized library like CMSISNN, designed specifically for low-power chips. These constraint stacks have a strict vocabulary of operations. Standard methods for tracking time in video, like recurrent neural networks, LSTMs, and attention layers, lack native integer support in these environments. If you force an unsupported recurrent layer onto a microcontroller, the system triggers a floating point fallback. It tries to calculate complex decimal math on a chip designed exclusively for simple integers, which instantly exhausts the available memory and crashes the device. You could strip out the recurrent layers and use purely spatial 3D convolutions instead. That avoids the operator error, but a full 3D convolution processing every pixel across every frame instantly overruns the SRAM limits. Functional offline sign language recognition requires rebuilding the architecture from first principles, mathematically factorizing spatial temporal processing so that every operation remains strictly within the limits of integer-only hardware. The S3D Conv1D architecture solves the memory trap by taking the heavy 3D convolution and physically splitting it apart into a 2D spatial plane and a 1D temporal line. The first stage ignores time. A two-dimensional spatial encoder analyzes each frame in isolation, scanning for geometric edges and hand contours. Max pooling operations then step in, shrinking those spatial activations down to a fixed resolution and compressing the visual data from each frame into a flat, one-dimensional array. Those individual arrays stack side by side. Together, they form a rigid grid matrix that mathematically represents the full duration of the video. Now the architecture analyzes time. A lightweight one-dimensional convolution sweeps across the matrix, extracting the timeline of the motion without ever needing to recalculate the heavy pixel data. By extracting the motion features linearly, this process bypasses the need for unsupported recurrent networks or memory-heavy attention mechanisms. Separating the calculation of what the hand looks like from the calculation of how the hand moves prevents the exponential memory overload that usually breaks edge devices. We can prove this efficiency using Big O complexity analysis, which measures how an algorithm's resource demands scale as the input grows. For embedded deployment, predictive scaling is a strict requirement. The parameter count for the spatial blocks is fixed. It is O of 1. It requires the exact same amount of memory regardless of how many frames you feed into the video sequence. The temporal layer only processes the pre-flattened feature arrays. This means its computational cost scales strictly linearly with the length of the video, O of t. The only component that scales with the size of the sign language vocabulary is the final classification layer, making it O of k. Adding those together gives a total spatial and temporal inference complexity of O of t plus k. It guarantees the predictable latency and strictly bounded memory usage required for microcontrollers. To actually fit on that microcontroller, the neural network's weights and activations must be reduced from decimal floating point numbers into 8-bit integers, a process called quantization.
This diagram shows how affine int8 quantization forces highly precise floating point values into a rigid integer range, bounded between -128 and +127. If the calibration range is pulled too far apart, the step size between integers becomes too large, and critical decimal data slips through the widened gaps. But if the range is narrowed too tightly, the mathematical tails of the curve are clipped off entirely, destroying the model's accuracy. Engineers use quantization-aware training to prevent this degradation during the model compilation process. But this training process is mathematically blind. It sets the scale and zero-point limits by running a calibration dataset through the model to observe the activation ranges. Even a mathematically perfect edge architecture will lose its predictive power if the specific dataset used to calibrate its integer ranges fails to represent the real-world inputs it will encounter. In Ghana, the SignTalk project builds AI systems to break down communication barriers in healthcare clinics. If you calibrate an 8-bit model for a patient in Kumasi using a dataset of American Sign Language, you introduce asymmetrical calibration drift. The motion dynamics differ, the mathematical ranges misalign, and the system fails to recognize the patient. Successfully building offline edge AI requires bypassing standard internet scraping and building domain-aware, hyper-localized datasets directly with the target community. For SignTalk, that meant physically collaborating with deaf individuals and healthcare workers across Ghana to collect and annotate 10,000 specific healthcare-related Ghanaian Sign Language video samples. When the S3D Conv1D model is calibrated with this localized data, it compresses down to 883 kilobytes and just 24 kilobytes in its ultralight variant, while maintaining 98.7% integer-based accuracy. Achieving true real-time offline edge deployment is only half an architecture problem. It is equally a localized data collection problem. As developers massively scale their datasets to train these models, the push to standardize data for machine learning creates a tension with linguistic diversity. National languages like Ghanaian Sign Language were largely formalized in the mid-20th century, heavily adapted from Western systems to create a standardized curriculum. Beneath those standardized systems exist deep, multi-generational indigenous sign languages. These original languages hold vital local knowledge regarding medicine, law, and family history. Consider the Adamarobe Sign Language in eastern Ghana. Pressured by standardized national signing, the population relying exclusively on the indigenous Adamarobe language has been whittled down to roughly 35 individuals. If technologists only collect data and optimize edge models for broad, standardized national languages, they build functional tools while accelerating the extinction of indigenous knowledge. The future of inclusive artificial intelligence rests on solving both equations. We have to mathematically compress the architecture to run on offline hardware, and we also have to ethically curate hyper-local datasets that serve the community without completely paving over their native languages.